Language models are trained on large text corpora that often include stereotypes. This can lead to bias in downstream applications, like in this machine translation tool. Here I just entered a Turkish sentence, which the tool translates to "she is a nurse" in German, but in Turkish this sentence is actually gender neutral. If I now just change the word nurse to doctor, the translation changes to "he is a doctor" in German. I showed this example in German because in English this tool already mitigates the bias by suggesting a female alternative, even though not quite consistently yet. In order to mitigate bias, it is necessary to know which bias actually exists in the trained model. A way to measure bias in contextual word embeddings is through the mask prediction task. The logarithmic probability bias score predicts the probability of woman being masked in the sentence "the hairdresser is A." In addition, this score computes a prior probability by masking both hairdresser and woman. This compensates for the fact that some targets are more common than others and would therefore always lead to higher probabilities. As for other bias measures, the user has to specifically probe for an expected bias. To explore potential bias more openly, visualization can help. To the best of our knowledge, the only visualization technique that shows bias in contextual language models is this work by Adam Pearce. This scatterplot shows the likelihood of Jim and Jane working in different occupations. The sentences can be changed by the user. Like prior work on bias visualization, this visualization only shows a set of targets, here occupations, against two extremes, here gender, defined by the two names. What we do not see here is the interaction between multiple bias dimensions, such as traits associated with different occupations and beverage preferences by people associated with different traits. To explore such interactions, it is necessary to go beyond showing the bias with respect to two extremes. We rather need to visualize multiclass bias. The design goals of our work therefore were that we wanted to support interactive exploration of multiclass bias, such as preference for multiple beverages against multiple occupations, supporting users to discover potential indirect bias between a seemingly neutral attribute and a sensitive attribute, and to help users reason about the sensitive attributes that may cause this bias. To support discovery of indirect bias, we need to work with slightly more complex template sentences for the bias prediction. The problem with more complex template sentences is that the context association may get lost. To circumvent this problem, we introduce an extension of the logarithmic probability bias score to detect indirect bias. The idea is to split up the sentence into two short statements and link them with a bridge. As bridge, we chose first names, since they are known to have a strong association with concepts like career and family. Specifically, we used the most popular baby names given in the US between 1920 and 2020. In total, these are 779 given names. Here we want to test the association between hairdresser and woman. Our score gives us two probabilities for each bridge element. To get the final score, we compute the correlation between the two probabilities for each bridge element. Intuitively speaking, if the probability of being a woman is high for names that also have a high probability of being a hairdresser, the score is high. Conversely, if the probability of being a man is low for those names that have a high probability of being a hairdresser, then the score is low. In our work, we support the interactive exploration of multiple multiclass bias categories, such as occupations, beverages, sports, and mental and physical traits. In addition, we added sensitive attributes like gender, country of origin, and age. To visualize bias, we provide two simple visualizations. We let users define a target attribute combination and show the computed scores as table. Each table cell corresponds to a correlation which is mapped to a diverging color scale. We can also interpret the predicted attribute scores as high-dimensional feature vector and perform dimensionality reduction. This way, we can show all target concepts as 2D scatterplot, where the proximity between two target concepts indicates their similarity with respect to the associated attribute, in this case, gender associations. The visualizations are interactive. If we want to inspect the preferred beverages associated with people working as waitress, we can click on the column once. This sorts the preferred beverages. On the top, we see the most associated beverages like milk, juice and tea. On the bottom, we see the least associated ones like beer and whiskey. If we click the column once more, the occupations get sorted by their similarity to waitress with respect to preferred beverages. Here we can see that nanny and hairdresser are most similar, pilot, captain and soldier are most dissimilar. Table sorting is persistent so that we can keep the sorting according to waitress and switch to the sensitive attribute gender. This shows that waitress is also strongly associated with female associated words. In the scatterplot, we can see the similarity of occupations with respect to their predicted beverage preferences. In other words, occupations that are close together have similar beverage preferences. The color was chosen for milk preference. To explore if a sensitive attribute can explain the similarities of occupations with respect to beverages, we can choose it for color mapping. Here we see that the association with female leads to a systematic color change with respect to the layout. This indicates that the sensitive attribute gender can explain the beverage preferences predicted for the different occupations. How does this compare to the results of the original logarithmic probability bias score? Here we see a comparison between the original direct bias score in the bottom table and our indirect version on the top table. We see beverages sorted by predicted preference by women. Our indirect score on the top sees a strong association between tea, milk and milkshake with woman and a negative association with liquor, whiskey and beer. This is consistent with girl and female and opposite to man, boy and male. The direct score on the bottom sees champagne, whiskey and wine most positively associated with woman and tea, soda and milkshake negatively associated. Interestingly, we get very similar predictions for men, but very different ones for girl and female. We compared these results with a study about alcoholic beverage consumption by gender. The indirect bias score reflects the findings of the study very well. A particularly interesting result was the most preferred beverage predicted for farmer. The indirect score predicts whiskey, the direct score predicts milk. For firemen, our indirect score predicts beer, the direct score predicts water. This is an indication that indeed the context drink may have been lost. There are also cases that do not work so well for the indirect bias score. We did a short qualitative study with 10 people, and some findings seem rather implausible to the users, like associations with sexual orientation. Intuitively given names of our bridge just do not predict sexual orientation. Country associations are also not so stable. For instance, our score would predict that people living in Austria are very unpopular. Some people in Austria would disagree with that. Here we can confirm that origin and race predictions by the indirect bias score are indeed unreliable. For instance, it would predict United States, Vietnam and Japan as the countries with the highest association with Hispanic people. The direct score predicts South American countries instead. One problem is that the names of our bridge set are currently very US focused. Apart from gender, a sensitive attribute that leads to very consistent results is year of birth, here predicted by beverage preference. By scrolling to recent years, we can observe how the popularity of energy drinks and vodka increased. Cider, tea and whiskey seem to be less popular for younger people. To conclude, we presented a new indirect bias score and 2 visualizations to explore multiclass bias, as well as interaction techniques to discover indirect bias. To get better results for country and race predictions, more international names would be promising. Our short study also showed that reasoning about potential sources of bias requires some training in both interfaces. Users would need more guidance here. The use of visualization quality metrics could be a first step for more guidance. With that, I thank you for your attention. You can follow the link and you can find both interfaces online.